So hello, welcome to this screencast on why you should use Rust. My name is Nicholas Matsakis. I'm a member of the Rust core team, and this is kind of my extended elevator pitch for why I think Rust is so cool. Well, in the past, if you needed to get real control out of your machine, make the most of its resources, you only really had one good choice, C or C++. And this is what we often call systems programming, right? Coding in an environment where you have limited resources and you need to make the most out of them. And we often think of this as being a kind of expert domain, but really it's a problem people hit with all levels of experience and in any language. You're just as likely to run up against resource limits when you're building your first Rails app, maybe even more likely, I would say, than when you're developing a purely C++ code base. Now, C and C++ were the languages of choice here because they offer great power. If your machine is capable of doing something, then you can code it up in C or C++, right? But as the saying goes, that great power comes with great responsibility. Any small mistake can easily have catastrophic consequences. At best, you might get a crash. At worst, your program will do something completely unexpected or open you up to a security vulnerability. And this is exactly why systems programming has come to have this aura of being a real superhero endeavor. And this is where Rust comes into play. So our slogan, as you can see here, is hack without fear. What we mean is, you should be able to do all those things that used to require C or C++, but you should do them in Rust, where the compiler and the language have got your back. And those same kinds of mistakes that once led to segmentation faults will now typically lead to compilation errors, so you can fix them up front. And the really interesting thing about this is that it starts to open up new horizons. It means that you can write programs or try things you would not have even considered writing before, because they were too difficult or too risky or just too much of a maintenance burden. Let me give you some examples. Here's some Ruby code. This is a Ruby method called blank. It's in the standard library. It checks if a string purely consists of white space. It does it with a regular expression. It's pretty simple, but as you might expect, it's not all that fast. So on the machine where we did some benchmarks, you could see it got about 1 million iterations per second. That might seem like a lot, but at some point it was found in a lot of Ruby on Rails apps, this is actually fairly high on the profiles. Right? It's a kind of a big hotspot. So in response to that, Sam Saffron decided to rewrite this function in C, and this is what he wrote. And you can see it's a lot more complicated, but it starts to pay off, right? Because before we got 1 million iterations per second, using this C version, you got 10 million. So that's like a 10x performance improvement. So by the way, if you used Ruby on Rails, you might want to get this FastBlink package. The thing is that writing C code like this is quite a big investment. Not only is the code really complicated and hard to get right, it has a lot of special cases for Unicode and so forth, it actually carries a lot of risk with it. This is raw C pointer handling. If you make a mistake here, anything could happen, right? So maybe if you're writing your own Ruby code and you don't have Sam Saffron to rewrite it for you, you might stick with this Ruby method and think it's not worth micro-optimizing this. It's not worth it. But what if you tried to use Rust instead? Right, so these were the performance numbers we saw before. If we use Rust, we would see this is an example of how you might write that function in Rust, and you can see it looks a lot different than the C code. It's a lot more higher level. It starts out by getting a string slice from the buffer, so this is a kind of subset of a string, and then it creates an iterator that yields up every character in this slice one by one, and it uses the all function, which takes a closure and applies the closure to each character. In this case, the closure tests if it's white space. So this will be true if all the characters are white space. Okay, so you might think, well, this looks nice, but it's probably not going to perform that well. But it does. It actually performs just as well as the C code. So what's exciting about this is not only that you can get the performance of the C code, but that you can get it with this pretty nice, pretty easy to maintain code that's written purely in safe Rust. So it has all the guarantees that it won't trigger a security vulnerability and so forth. Alright, so let's look at one more example. Now you may have heard that parallel programming is very hard to get right. Well, Rust aims to change that, both by offering APIs that make it easy to write simple parallel loops, and by having a type system that prevents the most common mistakes. So let's start here. Here we see some sequential code. It's an iterator that iterates over a list of paths. And then for each path, it's going to load up an image off the disk. And finally, by calling collect, we'll create and return a vector to the caller. So we have a vector of the loaded images. Now this is obviously something we could do in parallel. There's no connection between these different images. So how would we do that? Well, we can do this really easily by making use of a third-party library called Rayon. So this happens to be one that I wrote. When you write extern crate in Rust, that's kind of a signal of linking in a third-party library, which we call a crate. And now I can take my function and I can simply replace the .iter with .pariter. And what I get back is, instead of a sequential iterator, I have a parallel iterator that's going to execute in parallel. Now there's a couple cool things I want to note here. First of all, it's very cool that Rayon is just a library. This is not part of the core language, but it's able to do these powerful and fundamental extensions. And Rust is really designed around this idea of a minimal core that's extended by powerful libraries. And for parallelism in particular, we have worked hard to make sure that the core Rust language can support a wide range of parallel programming paradigms. It's because parallelism isn't really a one-size-fits-all affair, right? So Rust offers, for example, these parallel iterators that make it easy to do data parallelism across your for loop. But we also have things like tasks and channels that are kind of like Go or Erlang, shared data with mutexes if you need that, and a number of other options. So things like non-blocking data structures are in the works and so forth. Now, there's one more aspect though, because making parallelism accessible is not just about slick-looking APIs. You can find those in a lot of languages. What makes Rust different is that the type system can actually help and detect the kinds of subtle bugs that occur in parallel code before they make your code go haywire. All right, so let's see what I mean. Imagine here's a modified version, and you see it's different because it's going to be counting as it goes the number of JPEGs that it's loading out of the folder. Now the problem here is that this code is actually wrong. It has a subtle mistake. If you increment a counter like this with just a plain old +=1 on two parallel threads, this will cause a data race. The problem is, let's say the two threads might both read the current value, let's say it's 1, and then add 1 at the same time. So now they both think the next value is 2, and then they both store back, and your final counter went from 1 to 2, but it should have gone from 1 to 3 because there were two threads incrementing it. That's a kind of very simple sort of data race, and the biggest problem with this, or one big problem with this, is that if you run this code on a directory of, say, 500,632 images, your count is probably going to be close but not quite, right? So it might be 500,650 or 620 or something. And are you going to know the difference? You might. You might notice every time you run it, it comes up with a different answer. But you might also not notice and just keep going until it shows up somewhere down the line. So what would happen in Rust if you ran this code? Well, we'll never know the answer to that question because you can't run this code in Rust. It simply won't compile. Because Rust, the compiler, will detect that you're trying to have access to this variable from two different threads. And you can fix this either by moving that count out of the parallel loop, like maybe to a separate loop, or by using a shared counter that's safe across threads, like an atomic integer or mutex. So, now a language is really about more than just syntax. Part of being a modern language these days is making it trivial to incorporate third-party libraries. So we've made sure to have a strong package management story from the get-go. Rust offers a central repository of packages called crates.io and a powerful build tool called Cargo that can automatically download and build your dependencies for you. And Cargo basically replaces Make as the build tool of choice. And something else that we've tried very hard to do with Rust is to build an open and welcoming community. And this means a lot of things. It means that we both try to learn from one another as well as to teach one another. And that's what this slide, which comes from Julia Evans' keynote at RustConf this year, 2016, kind of gets across. I really liked it. I really like the way this slide shows that message in such a simple way. But we also have kind of open and welcoming up at the higher levels as well. So we have an open governance model, for example, where all our new features are publicly discussed and debated and improved. And of course, the project is open source and has been since its inception. So you can also just contribute code and so forth and take part in the development and leadership of Rust at all levels.